All right, welcome to The Explainer. Today, we're diving into the AI architecture that, for the first time, gave machines a form of memory. This is the key to how they understand language, music, really any kind of sequence. So let's get right into it. Think about this for a second. For you and me, this is easy. But for a machine, it's a huge problem. In both sentences, the word fine looks exactly the same. The only way to get the real meaning is to remember the words that came right before it. And that, right there, is the fundamental challenge of processing pretty much any sequence. This really hits the point home. A word's meaning depends entirely on its context. A standard computer program, one that just looks at one word at a time, would be completely lost. So how on earth did AI solve this puzzle? So here's our game plan. First, we'll talk about why machines needed memory in the first place. Then we'll get into the big idea behind recurrent neural networks. We'll peek under the hood, see how they actually learn, and finally, check out where they're living out in the wild. Okay, so let's start with the core problem. Your traditional neural networks, the ones that are amazing at, say, recognizing a cat in a photo, have a major blind spot when it comes to sequences. Yeah, they basically have the memory of a goldfish. For a standard network, every single piece of data, whether it's a word in a sentence or a note in a song, is a brand new, totally isolated event. It has absolutely no memory of what it just saw. And that makes it impossible to understand the flow of information. So to fix this whole goldfish brain issue, researchers came up with a really elegant solution: the Recurrent Neural Network, or RNN for short. And here is the big idea, the secret sauce. An RNN takes the information from one step and literally feeds it right back into itself as an input for the next step. It's a network that's kind of talking to itself, passing along what it learned from one moment to the next. This loop, that is the magic ingredient. It's such a simple concept, but it's incredibly powerful. This little feedback mechanism is what allows information to stick around, to persist, creating this chain of memory that connects the past to the present. Now, to really get this, we can imagine unrolling that loop through time. So at step one, the network gets an input, like the word I'm, and it creates this internal memory, which we call a hidden state. Then, for the next word, feeling, it doesn't just look at the word feeling. It looks at two things: the new word and the memory from the previous step. It's just like passing a baton in a relay race. Each step gives vital information to the next one down the line. Okay, so we've got the big idea. It's all about the loop. Now let's pop the hood and take a look at the key parts that actually make this whole thing work. At every single step, you've got your input, which is just the current piece of data. Then you have the hidden state, and this is the really crucial part. It's the network's working memory, its little scratch pad. Then, of course, you have the output, which is what the network predicts. All of this is controlled by the weights, these U, W, and V things. Think of them as the adjustable knobs that the network learns to tune, deciding exactly how much to listen to the new input versus the old memory. And don't let this simple structure fool you. As the source material points out, this architecture is, in theory, incredibly powerful. It means that, in principle, an RNN can compute anything a universal computer, a Turing machine, can. That just goes to show how versatile and fundamental this whole idea of a recurrent memory really is. Okay, so we've got the architecture down, but how does it actually learn to make sense of a sentence or a song? Well, that's where the training process comes in. The key algorithm here is called backpropagation through time, or BPTT. It sounds complicated, but the idea is pretty intuitive. After the network runs through a whole sequence and makes a prediction, BPTT calculates how wrong it was. Then it works its way backwards through time from the very end of the sequence all the way to the beginning, figuring out which steps contributed most to the mistake and tweaking the weights as it goes. It's literally like retracing your steps to see where you made a wrong turn. Now, this process is super powerful, but it is not cheap. The computational cost, as you can see here, scales directly with the length of the sequence, represented by tau. So longer sentences or longer pieces of music require way more time and memory to train, because that error signal has to be passed back through every single step. To make training a little more stable and a lot more efficient, researchers use a really clever trick called teacher forcing. The idea is, instead of letting the network use its own prediction from the last step, which might be wrong, to inform the next one, we force it to use the actual correct word from the training data. It's really the difference between learning with a guide and then having to go solo. During training with teacher forcing, the network gets the correct next step every single time, which helps it learn the patterns much, much faster. But when it's time for testing out in the real world, it's on its own. It has to rely entirely on its own last guess to make the next one. It's kind of like learning to ride a bike with training wheels on, and then suddenly having to take them off for the big race. So, we've covered the why, the what, and the how. Now for the fun part. Where do these things actually show up in our daily lives? You might be surprised. Seriously, they're everywhere. Every time your phone suggests the next word while you're typing a text, that's probably an RNN doing its thing. When you use Google Translate, an RNN is processing that whole sequence of words to capture the meaning. They can summarize articles for you. They can even look at a photo and generate a sentence describing what's happening. So if there's one thing to take away from all this, it's this. Recurrent neural networks were a fundamental shift in AI. That simple, elegant loop gave machines a form of memory, and for the very first time, it allowed an AI to see the world not just as a bunch of scattered, random puzzle pieces, but as a continuous, flowing, connected sequence. But, and here's a final thought to leave you with, this memory is powerful, but it's also a bit fragile. It works great for short-term context, but what happens when the context you need is from way, way earlier in the sequence? How does a machine remember a crucial detail from chapter 1 when it's trying to make sense of the final page in chapter 10? Well, that is a whole other challenge, and a topic for another explainer. All right, well,